everyone, and welcome to today's presentation. I'm Tammy Diedrich, the Managing Editor of IBM Systems Magazine, and I'm the moderator for this event. Today's webinar is sponsored by MVS Solutions and is titled Breaking the Speed Limit, Automation is the Engine. Our featured speakers today are John Baker and Selby Shanley. John Baker is a ZOS performance specialist with more than 20 years of experience as a user and consultant. He's assisted many of the world's largest data center customers with their ZOS performance challenges. John has held subject area chair positions with CMG and is a popular speaker at CMG, Share, and IBM conferences. Selby Shanley is a principal designer and developer of ThruPut Manager Automation Edition and is MVS Solutions' resident subject matter expert. Selby is steeped in mainframe technology and is well known globally as a ZOS, JES2, and WLM expert. In this webinar, John and Selby will share how financial pressures have led to widespread use of resource capping and how automation can improve throughput and optimize systems resources. Following the presentation, we'll have a brief Q&A period, so please feel free to enter your questions in the question panel on your screen anytime during the presentation. Now, without further ado, thanks again for joining us today. And John, I'll turn the presentation over to you.
Thank you, Tammy, and thank you, everyone, for attending today. We have a very focused agenda, so let's get right to it. The theme of our session today is automation, how that automation is delivered with ThruPut Manager Automation Edition, or TMAE. Firstly, we'll discuss the impending challenge of CMOS CPUs and what that means to your workloads. While we can't control the physical limits of the processor, there are automation techniques we can implement to address this challenge. Then we'll discuss the various capping techniques available today. In particular, capping myth has been circulating recently, which has raised the ire of our technical expert, Selby Shanley. You'll definitely want to stay tuned as he clears the air in that department. Finally, we'll talk about capping demand, an innovative technique we've developed with TMAE to directly reduce monthly software costs while maintaining performance for your key applications. We expect to have lots of times for questions at the end, and we really look forward to your feedback. Since Gordon Moore made his famous prediction in 1965, we have enjoyed exponential growth in CPU performance. Year after year, as our workloads grew, we could count on that next upgrade giving us a healthy performance boost. We're being told those days are over. This slide is exactly what Kathy Walsh of IBM presented at the Enterprise Conference last month. So what does this mean for the performance of our workloads? To increase capacity, we will have to grow wide by increasing the number of CPUs in our environments. Like a road that has reached its maximum speed limit, we will add more lanes. But what happens to single-threaded applications like batch? They can only use one lane. Let's take a look at what that means. Here's an example of increasing the number of CPUs in an EC12 from the same processor family. Notice that while the total capacity in MSUs increases, the speed per engine, expressed in service units per CP, decreases. This is not new and is commonly known as the multiprocessing or MP effect. As processors are added in a shared environment, the overhead associated with ensuring data integrity increases. The effect on single-threaded batch applications is that they will slow down. Even though the total capacity of your machine has increased, the individual engine speed has decreased. We can't do much about the physical limits of the processor, but consider CPU time is only one component of the total elapsed time of a job. In many cases, the accumulated wait times in the system add up to more than the CPU time. Let's take a closer look at some of the more common sources of wait time. Here we have an overutilized fast food restaurant. The design doesn't prevent more people from coming into the restaurant even as the wait time gets out of control. The result is many people waiting in line, but no one getting fed in a reasonable amount of time. The same principles hold true in a computer system. If additional workloads are continually added to the system, even as utilization reaches critical levels, everything waits longer. Some users may have a comfortable feeling since they see their job has started, but like the customers in the restaurant, the job isn't going anywhere very fast. You can see from this queuing graph that at very high levels of utilization, the total elapsed time becomes 10 or 20 times longer. The CPU is working just as fast, but the wait time to access the CPU increases exponentially. As utilization approaches 100%, the wait time increases to intolerable levels, just like the packed restaurant. The key to peak throughput is to constantly manage the workload distribution against the rapidly changing utilization to maintain just the right amount of load. Related to utilization is balance. A system running at 100% is spending more time waiting than doing productive work. In the example given here, even though the system at 60% provides better service than the system at 80%, the exponential delays experienced by the system at 100% more than wipe out those gains. The physical limits of the processor apply here as well. In order to achieve peak performance, workloads must be balanced across the available resources. As with utilization, workload demands change too rapidly to manage manually. Now, Selby's going deep to explain how TMAE manages utilization and balance to automatically provide maximum throughput.
To avoid overloading, ThruPut Manager AE only adds batch workload when and where it makes sense. LPARs must have available capacity. This means either the LPARs are not using up their CPU entitlement by weight, or there are still unused CPU cycles on the KEK, of which the LPAR is able to take advantage. The service class in which a job will run must be performing well to avoid unproductive overloading, because everything works better when you avoid overloading. It is not important when a batch job starts. It's when it ends that matters. This is even truer with production applications, where one or more jobs may be dependent on the completion of another. Jobs end sooner in a TMAE managed environment. We did a benchmark that shows this in action. We ran over 1,000 jobs being submitted over several hours. These jobs had a mix of CPU and I/O load and were run in Workload Manager batch initiators and under TMAE. There were no job dependencies. Of course, the two environments were identical in every way: hardware, software, and service class definitions. No other work was running on the KEK. The result? TMAE ran far fewer jobs at once, starting many fewer initiators, and completed much more work. Here's the graph of the benchmark results. You can see that the work ran for hours. Workload Manager started 300 initiators, while TMAE automatically started only 25 initiators. After over 8 hours, ThruPut Manager AE had completed 200 more jobs. The only reason it didn't get higher is that we stopped submitting work. These results will be even more dramatic with workloads that make use of job dependencies. Many installations use manually controlled just 2 initiators. In that environment, you will often find that the machine either is overloaded or underutilized, since it's just not possible to be as effective manually as automation that is constantly monitoring the environment, making decisions, and taking action. Sometimes less is more. By avoiding overloading, TMAE gets more batch jobs done faster. Overloading is much more likely in systems that are capped, which is why automation is so important when managing demand in a soft-capped environment. In order to balance batch workloads automatically, TMAE makes sure it is aware of the performance and capacity of the entire environment. It tracks the utilization of all LPARs and the required system and resource affinities of all batch workloads. The installation-specified business priorities are defined to TMAE so that it always selects the most urgent job. Workload is balanced automatically because ThruPut Manager AE controls the number of initiators on each system and dynamically spreads the workload across all members of the JESPLEX. Balancing is not simply making sure the same number of jobs are running on each system. Balancing means that each system in the JESPLEX runs the right amount of batch workload for the current conditions on each system, while still respecting any specific system affinity and resource requirements of individual batch jobs. ThruPut Manager AE considers the actual activity on each LPAR and reevaluates CAC, LPAR, and service class performance every 10 seconds so it can respond to environments that can and do change very rapidly. Only automation can do this. TMAE avoids overloading by rebalancing the batch workload as CPU demand and availability change. Capacity can change suddenly too, due to capacity on demand, LPAR weight changes, and soft capping. By balancing batch workload intelligently, ThruPut Manager AE delivers increased throughput with proper use of existing resources.
So let's talk capping. Well, why do data centers cap anyway? These folks certainly appear to be having a difficult time keeping a lid on things. Deciding to use capping means making a conscious decision to lower your capacity levels, thus increasing your utilization levels. Now, we just talked about the risks of high utilization levels, so why take that risk? Of course, this is why. Software is the largest operating expense in the data center. While subcapacity pricing allows billing based on peak consumption, running without caps means a spike in the rolling 4-hour average can lead to unacceptably high software bills. Caps provide the ability to control this cost, but at a price to performance. Caps are also referred to as capacity limits. As I mentioned, their primary purpose is to control monthly software charges by limiting the rolling 4-hour average. Hard caps limit application CPU consumption to the cap level at all times. This means the rolling 4-hour average can never exceed the cap limit. Soft caps only limit application consumption when the rolling 4-hour average exceeds the cap level. This chart shows the total MSU demand in each RMF interval and how it's constrained with a hard cap limit. Neither the application demand nor the rolling 4-hour average is ever allowed to exceed the set limit. It's just like having a smaller machine. This ensures very consistent software bills, but can be rather unforgiving to application performance. This chart shows the interval demand as well as the rolling 4-hour average with a soft cap in place. The application demand is freely allowed to exceed the cap limit because the rolling 4-hour average does not exceed the limit. As you can see, this option provides much more flexibility to application performance. Now, soft caps come in two varieties: defined capacity, which works on a single LPAR, and group capacity, or LPAR groups, which works on multiple LPARs on the same machine. I mentioned at the beginning that there's some confusion around how group capacity works. Selby's going to address this question now.
Before we talk about capping any further, let's clear up a misconception that when a group capacity limit is reached, the share of the limit for each member of the LPAR group is somehow fixed or frozen, and that LPAR groups are inflexible. This is absolutely not true. Let's look at how LPAR groups really work. When the rolling 4-hour average for an LPAR group exceeds the installation-specified group capacity limit, the group as a whole must be capped. But PRISM only knows how to cap LPARs. So what actually happens is that each individual LPAR is capped as required to keep the rolling 4-hour average for the group within the limit. In order for each LPAR to be capped, Workload Manager has to divide up the group capacity limit among the LPARs in the group, setting a limit for each LPAR. On each LPAR in the group, Workload Manager is monitoring the rolling 4-hour average of the group and the CPU usage of each LPAR. Workload Manager continually recalculates the share of the limit for each LPAR in several stages. Let's step through it. First, Workload Manager determines the share of the limit to which each LPAR is entitled by its weight as a percentage of the total weight of all the LPARs in the group. Second, Workload Manager identifies those LPARs that need more than their share, to which they are entitled, and also those LPARs that are not currently using all of their entitlement. Workload Manager simply lowers the share for those LPARs that don't need it all, and then divides this available capacity across the LPARs that do need more. This is a very familiar Workload Manager strategy called receiver donor, where Workload Manager moves CPU resource to where it is needed. On each LPAR in the group, Workload Manager sends a request to Prism to change the limit for the local LPAR, the one on which it is running, and telling it to cap the LPAR. Workload Manager tracks the CPU usage of the LPARs in the group and adjusts the individual limits constantly. LPAR groups are far from static. As the demands of each LPAR change, the limit for each LPAR is adjusted, making it truly dynamic. ThruPut Manager AE takes advantage of this, as we'll discuss shortly. Oh, and one more thing. For those of you interested in the technical details, I highly recommend reading an IBM document on capping, part of IBM's Inside Workload Manager series. And here you can see the URL. In this document, IBM developers explain how the capping limits are set for the individual members of the LPAR group. There's lots of other good information on capping as well. Now, don't worry. We'll show the URL again on our final slide, so you'll have lots of time to copy it down.
Now, we understand this is actually a very popular subject, so we had a poll prepared, and if I can ask IBM now to put that up for you, we're interested in your thoughts on capping. So we'll just leave that up for a couple of seconds. We'll continue on. Feel free to answer that poll, and we will go from here. So why isn't everyone capping? As we mentioned at the beginning of this section, capping without any way of managing your workload demand can be risky. Firstly, the idea may require a conversation with your application folks. Given that most are generally not open to risking application performance, those conversations may be difficult. Of course, capacity planning doesn't want to risk slowing things down either, so they'll want to set the limits fairly high. Finally, if your limits are too high, you're defeating the purpose of capping at all, which is to reduce costs. And of course, hitting the wall can indeed impact critical applications. Let's take a look at that effect. When the rolling 4-hour average does exceed the cap limit, applications are immediately affected. When this occurs, the LPAR, or group of LPARs, is capped by Prism. CPU resources are only provided to the LPAR at a rate that does not exceed the capacity limit, regardless of the actual application demand. The effect is very much as if the applications are suddenly running on a smaller machine. Further, the capping will remain in place until the rolling 4-hour average is back below the capacity limit. In this case, the effect remained for 3 hours. So what do we do when cap limits are exceeded? I worked in performance for a long time. We turn to our monitors, figure out who's consuming the most CPU. We cancel jobs, adjust priorities, basically do our best to help our applications continue to perform in a more constrained environment. Requires a lot of expert staff, and with the extreme cost of downtime, you usually can't hold out for very long. Availability is job one in a mainframe environment, so often we have to resort to raising the cap. While this provides a positive effect on our applications, it may establish a new peak rolling 4-hour average for that month. There's really no point in putting the cap back down, as the software bill is based on the highest peak. To recap, when the rolling 4-hour average hits the capacity limit, the entire LPAR is capped, potentially affecting all applications on the LPAR. Rather than allow this to occur, TMAE allows you to only cap specified batch workloads. Further, TMAE takes a soft hammer approach by gradually reducing or deferring the CPU consumption of the batch that you designate, preventing you from hitting the wall. Many shops are under the mistaken impression that batch does not impact their peaks because it runs at lower priority or it runs at night. It's simply not true. Firstly, bear in mind that all workloads contribute to the rolling 4-hour average, regardless of priority. A CPU second is a CPU second. Secondly, consider the following chart. This chart was generated from actual customer data and only reflects the day shift. While online is certainly the dominant contributor, note that batch makes up a significant portion of the rolling 4-hour average. Even a modest reduction in batch consumption during these peaks can yield significant software savings while maintaining performance of your key workloads. This chart goes a little deeper by further breaking the batch workloads down into high, medium, and low priority. As you can see, the low and medium priority batch makes up 24% of the rolling 4-hour average peak. That is 24% of your monthly peak MSUs. Now, we already know that TMAE has the knowledge and ability to control workload based on utilization, priority, and balance. Now Selby's going to explain how TMAE allows you to lower your peak MSU consumption by capping demand.
In order to cap demand at the right times, ThruPut Manager AE has to understand the environment and be aware of any changes that may occur. Of course, TMAE determines if there are any defined capacity or group capacity limits set by the installation, and will detect any changes made to these limits. It also tracks the current rolling 4-hour average CPU usage for each LPAR and the current CPU demand. It's important to keep current demand in mind when making decisions on whether or not certain workloads should be increased. In order to have a full picture, TMAE also tracks the overall CPU consumption of the KEK and each LPAR in the KEK. High CPU consumption by one or more LPARs can affect CPU availability for other LPARs. ThruPut Manager AE monitors batch workload performance to avoid overloading leading to poor overall performance and delays. This is particularly important when capping demand so that the workload being capped still performs as well as possible given that it is being constrained. TMAE caps the batch workloads chosen by the installation in 3 phases. First of all, as the rolling 4-hour average increases and approaches the limit set by defined capacity or group capacity limit, TMAE automatically starts restricting the CPU consumption by these workloads. It does this in 5 gradual steps. The idea is to slowly shrink usage and avoid hitting the limit with very high CPU consumption. We usually refer to this as hitting the wall. When you become soft-capped at high rates of CPU utilization, this sudden drop in CPU availability can significantly affect performance. When this happens, this usually causes installations to immediately increase their limits and their software bills. By taking action in 5 steps before the limit is reached, ThruPut Manager AE makes capping manageable and eliminates the negative performance effects. Then, while soft capping is occurring, TMAE continues to constrain the lower priority batch workloads to the maximum extent specified by the installation, reducing the overall CPU demand in each affected LPAR. This leaves more cycles available for high priority workloads, such as online, even if the high and low priority work are on different LPARs. Once the peak passes, the LPAR is no longer being capped, and overall CPU consumption begins to come down. ThruPut Manager AE starts to smoothly remove the constraints on the affected batch workloads, gradually allowing more access to CPU, reversing the 5 steps that I just talked about. The goal is to automatically get as much of the deferred workload running as quickly as possible, as long as the rolling 4-hour average is not increased, a difficult task without automation. Gradually, TMAE starts to run the deferred jobs. As long as the rolling 4-hour average does not increase, the constraints will be relaxed further, and more of the deferred batch workload will be allowed to run. ThruPut Manager AE also makes sure that the deferred work is selected at a rate that does not overload the LPAR. TMAE makes it possible to live not only with the caps you may currently have implemented, but to reduce them further while still protecting the performance of your high-priority applications. Lower cap values translate directly into lower software bills every month going forward. Here's a couple of examples to show how this all works. Here's an example of an LPAR group with 2 LPARs, LPAR 1 and LPAR 2, with a mix of online and batch load. On the left, before using ThruPut Manager AE, the total peak rolling 4-hour average is 2,200 MSUs per hour. After implementing TMAE, the installation decides that 25% of their batch should be eligible to be deferred. The results? The online usage remains the same, while the batch is smaller for a new total peak rolling 4-hour average of 1,975 MSUs per hour, a saving of 225 MSUs per hour. The group capacity limit can be reduced by 225 MSUs per hour without affecting online performance. As the demands of the reduced workload on the 2 LPARs varies, Workload Manager will adjust their individual shares of the new lower group capacity limit accordingly. In this second example, we have a different configuration, an LPAR group with 2 LPARs, 3 and 4, one of which, LPAR 3, has mostly online, and a small amount of high-priority batch that must run on that LPAR, and another, LPAR 4, that runs entirely batch load. On the left, before TMAE, the peak rolling 4-hour average for this LPAR group was 1,850 MSUs per hour. This installation wants to reduce their peak monthly rolling 4-hour average, but they have also reached a point where their online applications are going to need more CPU to handle an expected increase in transaction volume due to the introduction of a new application. These are usually conflicting goals. The installation identifies 300 MSUs of batch workload on LPAR 4 that can be deferred during peak times. They decide to reduce their LPAR group limit by 200 MSUs per hour and let the online work on LPAR 3 consume an additional 100 MSUs per hour. Note that the batch on LPAR 3 is all high priority, so they left it alone. Thanks to ThruPut Manager AE reducing the batch workload, Workload Manager on the 2 LPARs is now able to adjust the shares of the group capacity limit so that LPAR 3 gets 100 MSUs per hour more. The installation's online applications got the needed capacity boost, and they still reduced their peak monthly rolling 4-hour average.
Getting back to our example of soft capping, let's drill in on the peak and show you the effect of capping demand on your software bill. This is a zoomed-in view of the previous chart's peak period. As you can see, the rolling 4-hour average peak of just under 300 MSUs per hour occurred shortly after noon. What we can further see, however, is that the seeds for that peak started hours before, when the demand started pushing the rolling 4-hour average higher. We have already seen the effects of hitting the wall, so we don't want the limit to be lower than the rolling 4-hour average peak. Lowering the demand directly lowers the rolling 4-hour average and the software bill. AE is aware of the cap limit, the demand, and the rolling 4-hour average. By proactively reducing the demand as the cap level is approached, TMAE lowers the software bill while avoiding hitting the wall. Further, you now have the opportunity to lower your cap limit, and AE will automatically adjust. You can repeat this approach to find the sweet spot where SLAs are met for the lowest possible cost. You're probably wondering how AE could help in your shop. If you send us your SMF data, we'll identify your rolling 4-hour average monthly peaks and calculate the batch MSU contribution to those peaks. By then applying your installation MLC rate, you can easily determine your potential savings. You can then decide to put those MSUs directly into MLC cost reduction or re-provision the capacity elsewhere. Again, we understand that everyone has different MLC rates, so we do have another poll, if you wouldn't mind, if IBM could put that up for us. And we'll leave that up for a few seconds, give you an opportunity to answer. However, at this point, that is all we had for the material. I'll pass the mic back to IBM, and we are happy to take your questions.
Great, thanks so much. So we'll take just a few minutes. Okay, first question. We are already using LPAR groups for capping. How can ThruPut Manager help us further?
Well, as we were discussing in the examples there, what ThruPut Manager does by reducing the demand is going to allow you to lower your cap levels even further.
And I think another point that we could make, too, is the whole thing about not hitting the wall. So by backing it off before you actually soft cap, which is something that LPAR groups won't do for you or define capacity, we can slowly start braking before we hit the red light. And that means you can actually move the limit lower without suffering bad consequences of having too much load running, then all of a sudden everything being capped.
Great. Does ThruPut Manager only work with LPAR groups?
Oh, no, absolutely not. However, I'm going to let Selby elaborate on that. ThruPut Manager is quite extensive technology.
ThruPut Manager AE supports not only LPAR groups, but also defined capacities or a combination of those. So if you are using either of those or both, it all works, and it knows what the limit should be for any particular LPAR. It also supports people who have not implemented soft capping yet. And one of the things that we think is this can really help you implement soft capping, but you want to start out without, you can supply ThruPut Manager AE with a limit for each LPAR. This won't cause soft capping, but it will cause TMAE to behave as if that is the limit, and it will take all of the appropriate actions to slow down load as you get there. You won't be capped, but it will reduce the load as your 4-hour rolling average approaches that for the individual LPAR. And then it will start releasing that load as your average comes down. So it's a way to try it without actually implementing soft capping, and then when you're comfortable with the mechanism, you can and see where you're actually hitting, you can then start putting in an LPAR group limit, a group capacity limit, or a defined capacity limit.
All right. What levels of ZOS does ThruPut Manager support?
we support all releases that IBM supports of ZOS and JES2.
All right, great. Within this idea, would you dare mix LPAR types like test, sandbox LPARs with production LPARs?
Oh, absolutely. One of the great benefits of TMAE is that it works at a workload granularity level, which is what you're describing there with test and production workload. Rather than just working with the entire LPAR, you may have different flavors of work, if you will, different business importance, and TMAE is aware of the importance of the different workloads and can react accordingly.
One of the things to point out is, of course, that every single CPU cycle counts towards your rolling 4-hour average, so the test costs you just as much as your production. You can set them up in an LPAR group such that TMAE will automatically cut back on your test workload during peak times while allowing the production to go ahead, even though they're on different LPARs.
Okay, great. Well, I don't think we have any more questions unless some come in here just in the next few minutes. So I will say thank you so much, gentlemen, for sharing your expertise with us today. Just to note that we will be sending out a link later this week to a recording of actually it'll be early next week, to a recording of today's presentation to everyone on the call, as well as anyone who registered for today's event but for whatever reason couldn't make it. So that concludes our webinar. I want to thank everyone for attending and have a great day.